Hello, folks. At this point, we should have a good grip on the science behind chemical reactions. And we know how to write the reactions down in the form of balanced chemical equations. We are now poised to learn the fundamental chemistry math used in quantifying matter in reactions. This math is called stoichiometry and is the chemist's bread and butter, the computational method that we rely on when we work with chemical equations and when we try to measure out materials for reactions. Stoichiometry is a type of math utilized by chemists which involve calculations using conversion relationships between reactants and products in a chemical reaction equation to determine desired data. Stoichiometry completely relies on the law of conservation of mass, where the mass of the reactants and products are assumed to be equal. So it's critical that the chemical equations are balanced before we do anything else. Rule 1. Our first rule in doing any stoichiometry is to balance the chemical equation. Okay, we need a good reaction to work with to demonstrate the rest of our rules of stoichiometry. Let's use, once again, the synthesis-redox reaction of hydrogen and nitrogen gases combining to make ammonia gas. Rule 2. Our second rule involves using the balanced chemical equations to establish mole-mole relationships for use in problems. The stoichiometric coefficients in front of the molecules in this ammonia reaction set up mole-mole relationships between all the molecules. For instance, for every 3 moles of hydrogen used in our ammonia reaction, 1 mole of nitrogen is required in the reaction, and 2 moles of ammonia are produced. Or we could say for every mole of nitrogen used in the reaction, 2 moles of ammonia are made. These mole-mole conversions and relationships are only useful and work if the matter quantities are in the units of moles. Let's use these conversion relationships in some chemical problems. Okay, so assume we have 0.750 moles of nitrogen gas. How many moles of ammonia can we make? We're going from moles of nitrogen gas to moles of ammonia using our new relationships, where the stoichiometric coefficients in the chemical equations inform us that 1 mole of nitrogen is equivalent to 2 moles of ammonia. From the computation, we see we can make 1.50 moles of ammonia. Now, how many moles of hydrogen is required to make 0.37 moles of ammonia? We will use the balanced equation, and we see from the stoichiometric coefficients, 3 moles of hydrogen are equivalent to 2 moles of ammonia, leading to the computed result that 0.562 moles of hydrogen are required to make 0.375 moles of ammonia. If we're given information in mass, volumes of gas, or concentrations, the critical rule we need to follow is Rule 3. Turn all given quantities into moles, so the mole-mole relationships in the balanced reaction equation can be utilized. So if we're given masses of materials, we simply use the formula mass of the compounds to convert to moles of compounds. If we're working with ideal gases, we should be given enough information to use the equation of state, PV equals nRT, to take these given quantities and compute moles of gas, N. Many times we'll be working in STP, standard temperature and pressure conditions, which helps streamline the calculation a bit. Now, if we're working with solutions and know the concentrations, we can use the concentrations and volumes to help us compute the moles of the material. And if you have watched the previous videos described in the contents, you've already done all these computations before, so we're tooled to face all of these conversions. Now, before doing a few examples, we also need to establish one more rule. Rule 4. Answer the problem in the correct units. So we may have to do a little work after we have used the mole-mole relationships to turn the moles into a unit required by the problem statement. Okay, let's demonstrate the stoichiometry rules in some example problems. We have a chemical process where aluminum metal reacts with sulfuric acid to make an aqueous aluminum sulfate solution and hydrogen gas. What do we do first? We can't compute anything until we balance the reaction. All right, we now have stoichiometric values which give us our mole-mole relationships ready to be used when needed. Let's do some computations using this chemical equation. If I have 20 grams of aluminum metal, how many grams of hydrogen can I make? Now, if we follow a solution map from grams of aluminum to grams of hydrogen, it'll look like this, where we transition from mass of aluminum to mole of aluminum through the atomic mass, use the aluminum-hydrogen mole-mole ratio to find moles of hydrogen, and since the problem statement wanted us to find the grams of hydrogen produced, we need to convert to grams of hydrogen using the molecular mass of hydrogen. The computation line is shown, and we calculate a value of 2.25 grams of hydrogen being produced from 20 grams of aluminum. Now let's do a problem where we work with an ideal gas. How much aluminum in grams did I use if I made 5.00 liters of hydrogen gas at 25 degrees C and 1 atmosphere? Now we're going to assume the hydrogen gas is ideal. Now notice our solution map. We need first to use the PV equals nRT equation of state to solve for moles of hydrogen gas. We need to convert the given units of liters, degrees C, and atmosphere to SI units of meters cubed, Kelvin, and pascals to use the SI version of the universal gas constant R. This computation can either be done separately or done as shown here at the very start of the computation. The first 4 terms of the computation are doing just this. Once we know the moles of hydrogen, we use the mole-mole ratio to find moles of aluminum, and realizing we need the answer in grams, we finally use the atomic mass of aluminum to get to grams of aluminum. Putting everything into the computation line, following our map, we get 3.68 grams of aluminum. Now let's do a computation using solution concentrations. If I react 200 milliliters of 18 molar sulfuric acid in the chemical process, how many moles of hydrogen do I make? As always, we need to get to moles of sulfuric acid before we can use our mole-mole relationships. We will first convert milliliters of sulfuric acid to liters of sulfuric acid, and then using the concentration, 18 molar, which is equivalent to 18 moles of sulfuric acid per liter of solution, we can get moles of sulfuric acid. The mole-mole relationship of sulfuric and hydrogen gas will get us to our final answer. Putting in all the numbers, we find we can produce 3.60 moles of hydrogen from this reaction. Now, let's put everything into this next computation. What minimum volume in milliliters of 4 molar sulfuric acid and what mass of aluminum in grams is required to produce 5,000 milliliters of hydrogen gas at STP? Now, if we remember, STP means the temperature of the gas is 0 degrees Celsius or 273.15 Kelvin, and the pressure is either 1 atmosphere or 1 bar, depending on your textbook. For this example, we'll assume the pressure is 1 bar, which is equivalent to 100,000 pascals. Now, all we need to do is turn our volume of hydrogen gas to liters, and then meters cubed, and then we're good to calculate the moles of the hydrogen using N equals PV divided by RT. Computing this, we find we have made 0.220 moles of hydrogen gas. From here, it's rather straightforward to calculate the moles of sulfuric acid and milliliters of sulfuric acid required to make this much hydrogen, as well as moles of aluminum and mass of aluminum we would need to make the hydrogen. Look carefully at the solution maps of each of these reactions and work through the computation line to understand how each calculation was done. We find that we would need 55 milliliters of sulfuric acid and at least 3.96 grams of aluminum to make 0.220 moles of hydrogen. Again, be extremely aware of your significant figures and try not to round off too early in these multi-step conversion problems. Hopefully you can now see that the chemistry house is almost complete, and all our efforts in previous lectures have come together in these stoichiometric problems. Nothing really is new in this lecture. We're just taking all the separate computations from earlier lectures and gluing them together to get all the quantities required by the various chemical reactions we may encounter in chemistry. Be patient and review concepts as you need them. And as always, do as many problems as you can using different kinds of compounds, different phases of reactants and products, different concentrations of materials and mixtures, and different reaction types: precipitation, acid-base, and redox. Now, the next lecture video will expand our stoichiometry to include circumstances when we have too much or too little of some of the reactants, when our yield of the products has been compromised, so we don't get as much as we expected. And finally, what we must do if we want to quantify the endothermic or exothermic energy of the reaction. See you soon.